This call is now being recorded.
Good afternoon to all of you. Now we move towards a next system called link. The link system call links a file to new name in the file system directory. That is creating a new directory entry on for an existing inode. So link system call links. There is a linkage between file system directory and a file. So creating a new directory entry for existing inode. Then syntax for this system call is link. Then source file name and a target file name. These are the arguments. So source file name is name of existing file name, and target file name is the new or additional name file will have after completion the link call. So file system call contains a path name for each link the file has, and process can access the file by any of the path names. Suppose a file have number of path names which we can access. So here in this example, link, the file is a system, that is linkage is like this. uh, this is the original or source file name, that is user source uts and system. So for this test file has two paths, that is a source path as well as target path, that is user source uts system test file.h. This is the first path name. After linkage the path name will be like user include system test file.h. And for also a real file is path name is user include a real file. So kernel doesn't know which file name was original file name, so no file name is treated specially. So see, this is a structure for a linkage of file linkage. So following these three path names for see, for test file there are three path names. User, first path name is user source uts a system test file. See, in this example for test file there are three paths. Test file.h, this file have three paths. First path is user source uts system and test file.h. This is the original, but after the linkage in previous year, this test file is after the link command, the test file is stored to this include user include system. So here user include system, then go to the system and then test file. Then in previous slide we have seen that user link user include a real file.h. This is the source file. User include a real file.h. This is the source file name, and target file name is user source uts system test file.h. This is the target file name. So see here user user source uts system test file.h, and this is the target file name, and here user include real file.h, and this is test file.h. This is the target file name. So this test file.h have three paths. First is original as a source path, then after linkage link command is used here two times. First after system here, and a second time after real file.h. So kernel allows only a super user to link directories, simplifying the coding of programs that traverse the file system tree. If arbitrary users could link directories, programs designed to traverse the file hierarchy would have to worry about getting into infinite loop. If a user were to link a directory to a node name below the hierarchy, the super users presumably more careful about making such link. If arbitrary users, that is randomly any user could link directories, programs designed to traverse the file hierarchy worry about getting into infinite loop. If user were linked to directory node and below it in the hierarchy, but the super users are pre-assume that more careful about making such links. Capabilities to link directories had to be supported on early version of the system, because the implementation of make directory command, that is mkdir, which creates a new directory, relies on the capability to link directories. Inclusion of mkdir system call eliminates the need to link directories. This is the algorithm for linking file. Algorithm link input existing file name, new file name, that is target file name, and output is none. Get inode for existing file name with the help of algorithm name I. If too many links, that is number of links on file or linking directory without super user permission, then if this condition is true, then release that inode with the help of I put algorithm and return error. If this condition becomes false, then increment link count on inode. Update disk copy of the inode, unlock inode. Get parent inode for directory to contain new file name with the help of name my algorithm. If new file name is already exist in existing file system, or new file name, new file on different file system which is already exist. Then this this is a true. Then undo update done above and return error. If new file name is does not exist, then create a new directory entry in parent directory of new file name. Include new file name, inode number of existing file name, release parent directory inode with the help of IPUT algorithm, release inode of existing file name with the help of IPUT algorithm. This is the algorithm for linking files. So this algorithm for link, the kernel first locates the inode for the source using algorithm name I, increments the link count, updates the disk copy of inode, and unlocks the inode. It then searches for the target file. If the file is present, then link call fails and kernel decrement the link count incremented earlier. Otherwise, it notes the location of empty slot in the parent directory of the target file, writes the target file name and source file inode number into that slot, and releases the inode of the target file parent directory via algorithm by the use of algorithm IPUT. Since the target file did not originally exist, there is there is no other inode to release. So the kernel concludes by releasing the source file inode. Its link count is 1, greater than it was the beginning of the call, and the another name in the file system allows access to it. The link count keeps count of the directory entries that refer to the file and thus distinct from the inode reference count. If no other processes access the file at the conclusion of the link call, the inode reference count of the file is 0 and link count of this file is at least 2. For example, when executing the statement like link source is the name of source file and directory target is the name of target file, so kernel locates the inode of source, increment its link count, remembers its inode, suppose inode number is 74, and unlocks that inode. It locates the inode of the directory, the parent directory of the target files, finds an empty directory slot in the directory and writes the name file is a target with the inode number is 74 in into the empty directory slot. Finally, it releases the inode for a source via algorithm input. If the link count of source had been 1, now it shows 2. Two deadlock possibilities are worthy of note, both concerning the reasons of process unlock the source file inode after incrementing its link count. If the kernel did not unlock the inode, the two processes could deadlock the executing of following system call simultaneously. Suppose there are two processes, process A and process B. In process A, suppose a statement like link, then source file is a D, that is this is a path name. A is the root directory A, B, C, and D is the source name, and target file is suppose G, that is E, F, G. Similarly, process B executes the statement like EF is a source file and target file is A, B, C, D, and E, E. Then it then the kernel didn't unlock the inode. Two processes could deadlock executing by system calls simultaneously. Suppose these two statements. Suppose the process A finds the inode for file D, that is the path ABCD. At the same time, the process B finds the inode for the EF file. So both processes find the inode for these their source file. So the phrase at the same time means the system arrives at state each process had collected its inode. Suppose scenario, the deadlock scenario we will see here. Get inode for process A, release inode A, get inode. In case of process A, we are seeing here. Here suppose inode received for process A, then receive release inode from A, then get inode for B, then release from B, then get inode to C, then release from C, then get inode for D, and try to get inode for E. At that time, process B is trying for inode trying for E. So go to the sleep mode. Here, process A also go to the sleep mode, and after some time wake up, the inode E is unlocked. So at that time, suppose process B is wake up and receive inode for process E. Inode received for inode for file E, then release from E, then get inode to F, release, then get to the process A, and so on. But at that time, process A at the sleep mode until that process does not until the process has not received the inode which is free. So process A is locked, that is process A is locked for trying to inode E. This is a deadlock condition. So this figure illustrates that the when process A now attempts to find the inode for directory E and F would sleep awaiting event for the inode F becomes free. Here, see in this figure, in process A we are trying inode for file A, but in process B received the inode to E, and after releasing it receives to A. After releasing the inode receives to F, then after releasing it goes to the A, so that process A will execute the file E. So this is the deadlock condition. But when process B attempts to find the inode for directory ABCD, it would sleep awaiting event that the inode for D becomes free. The process A would be holding locked inode that process B wants, and process B would be holding a locked inode that process A wants. Process A would be holding and locked inode that process B wants, and similarly process B would be holding and locked inode that process A wants. So kernel avoids such a situation by releasing source files inode after incrementing its link count. Since the first source inode is free when accessing the next source, and so there is a no deadlock can occur, but in some situation deadlock condition may occur. So in this last example we have seen the two processes could deadlock each other if the inode lock were not released. A single process could also deadlock itself. Here the process here ABC is a source file, whereas ABCD is a target file. So it would allocate that the file C as from first part, that is from source, from the source. So first part of the algorithm, kernel didn't release the inode lock. It would deadlock when encountering inode C searching for file D. So if two processes or even one process could not continue executing because of deadlock, that would be effect on the system. What would be the effect on the system if two processes or even one process could not continue executing because of deadlock? Then what happens, or what would be the effect of the system? Since the inodes are finitely allocatable sources, receipt of signal cannot awaken the process from its sleep. Hence, system could not break the deadlock without rebooting. If no other process accessed the files over the process deadlock, and no other processes in the system could be affected. Then next system call is unlink. So unlink system call removes the directory for a file. Here a syntax for unlink system call is unlink and parameter is path name. The path name identifies name of the file to be unlinked from the directory hierarchy. If a process unlinks a given file, no file is accessible by that name until another directory entry with that name is created. Suppose the code like statement unlink and parameter is or path name is suppose my file, and another statement fd, that is open my file by other group read only. So open call should be fail because current directory is no longer contains in my file, that is there is no linkage, so that it cannot be open. If the file should be unlinked, the last link of the file, the kernel eventually frees its data blocks. And however, if the data had several links, it is still accessible by another names. So this is the algorithm for unlinking a file. So algorithm unlink, input a file name, output none. So so get parent inode of the file to be unlinked with the help of name algorithm. If unlinking the current directory, if last component of the file name is a dot, then increment inode reference count. Else get inode of the file to be unlinked with the help of iget algorithm. If the file is directory but user is not super user, then release inode with the help of iput algorithm and return error. If shared text file and link count currently 1, then remove from region table, write parent directory, 0 inode number of unlinked file, release inode parent directory with the help of iput algorithm, decrement file link count, and release file inode with the help of iput algorithm. Iput checks if link count is 0. If so, release the file blocks and with the help of algorithm free, and freeze inode with the help of ifree algorithm. So kernel first uses the variation of algorithm name I to find the file that it must unlink, but instead of returning its inode, it returns inode of the parent directory. It accesses the in-core inode of the file to be unlinked. Use algorithm iget. After checking error conditions and so far executable files, removing inactive shared text entries from the region table, kernel clears the file name from the parent directory and writing a 0 for a value of inode number suffixes the clear slot of the directory. The kernel then does a synchronous write of the directory to disk, ensure that the file is inaccessible by its old name. If it is not accessed, then decrement link count and release the in-core inode of the parent directory and unlinked file via algorithm iput. So when releasing the in-core inode of unlinked file in input, if the reference count drops to 0 and if the link count is 0, then kernel reclaims the disk block occupied by the file. No file name refers to the inode any longer, and inode is not active if it is removed or unlinked. So to reclaim the disk blocks, the kernel loops through the inode table contents and freeing all direct blocks immediately according to algorithm 3. For the indirect blocks, it recursively frees all blocks that appear in the various levels of indirection, freeing the more direct blocks first. It zeroes out the block number in the inode table of contents and sets the file size in the inode to 0. It then clears the inode file type field to indicate that inode is free and frees the inode with the algorithm ifree. It updates the disk since a disk copy of the inode still indicated that inode was in use. Now the inode free for assignment to other files. Then next is a file system consistency. So kernel orders its writes to disk to minimize the file system corruption in event of system failure. For instance, when it removes a file name from its parent directory, it writes the directory synchronously to the disk before it destroys the contents of the file and frees the inode. If the system were crashed before the file contents were removed, damage to the file system would be minimal because there would be an inode that would have a link count 1 greater than the number of directory entries that access it, but all other paths to that file to the file would still be legal. If the directory write were not synchronous, it would be possible for all directory entry on the disk to the point that is free or reallocated inode after system crash. Thus, there would be more directory entries in the file system that refer to the inode. That inode would have link counts. In particular, if the file name was that of the last link of the file, then it would refer to unallocated inode. System damage is clearly less severe and easier to correct in the first case. For example, suppose a file have two linkages with path names A and B. Suppose a process A unlinks process unlinks A path name A, and if the kernel orders a disk write operation, then it zeroes the directory entry for A and write to the disk. If the system crashes after write the disk completes, the file B has a link count 2, but file A does not exist because its old entry had been zeroed before the system crash. File B has extra link count, but system functions properly when rebooted. Now, suppose the kernel ordered the disk write operation in the reverse order and system crashes. That is, it decrements the link count of B to 1 and writes inode disk. and crashes it before it becomes 0. So directory entry for A. So when system is rebooted, the entries for file A and B exist in their respective directories, but link count of the file their reference is 1. If a process then unlinks a file A and the link count drops to 0, even though file B still references the inode. If the kernel were later to reassign the inode as the result of create system call, the new file would have link count 1, but two path names were path names that reference it. The system cannot rectify the situation except via maintenance programs that access the file system through a block or a raw reference. The kernel also the inodes disk blocks in a specific order to minimize corruption in event of system failure. When removing the contents of the file and clearing the its inode, it is possible to free the block containing the file data first, or it is possible to free and write out the inode first. The result is usually identical in both cases, but it differs if the system crashes in the middle. Then next part is a race condition. A race condition around the unlink system call. A race condition around the unlink system call, particularly while or when unlinking the directories. The rmdir, that is a remove directory. This command removes the directory after verifying that the directory contains no files, that is its value becomes 0. But since rmdir runs at user level, actions of verifying that directory becomes empty and removing the directory are not atomic. The system could do the context switch between execution of read and unlink system calls. Hence, another process could create a file in the directory after rmdir determined that directory was empty. Users can prevent this situation Users can prevent this situation only by use of file and record lock-in. Once a process begins execution of unlinked call, however, no other process can access the file being unlinked since the inodes of parent directory and file are locked. So the algorithm for link system call and however how the kernel unlocks the inode before completion of the call. If another process should unlink the file while inode locks is free, it only decrement the link count. Since link count had been incremented before unlinking the inode, the count would still be greater than 0. Hence, the file cannot be removed and the system is safe. The condition is equivalent to case where the unlink happens immediately after link call completes. Another rest condition exists in the case where one process is converting a file path name to an inode using the algorithm name I, and another process is removing directory into that path. This is unlink rest condition. Suppose there are three processes, process A, process B, and process C. Initially, suppose process B unlink file C, process B has started unlink file C, find inode for C unlock, find inode for C locked, so that it goes to the sleep mode. After some time, process A searches a directory B for name C, get inode number for C, and finds inode for C. Here, in first situation, process B also searches inode for C. Here, process A searches inode for C. In both situations, find inode for C, and that inode is locked. So both processes goes to the sleep mode. After some time, process B wakes up and see that the C inode is free, so unlinks that C, and old inode is free if link count is equal to 0. Then suppose process C is enters, then assign new inode to new file N, happens to assign old inode for C, eventually release the inode N is locked. After some time, process A wakes up and old C inode is free. So it receives that inode for N and search N for name D and so on. This is the race condition for unlink system call. So suppose process A is parsing the path name ABCD. It goes to the sleep while allocating in core inode for C. It could go sleep while typing to lock the inode while trying to access the disk block in which the inode resides. If process B wants to unlink the directory C, it may go to the sleep, possibly for the same reasons that process A is sleeping. Suppose kernel later schedules process B to run before process A. So process B would run to completion, unlinking the directory C and removing it and its contents before the process A runs again. Later, process A would try to access an illegal in-core inode that had been removed. The algorithm name I therefore checks that the link count is not 0 before proceeding, reporting an error. Otherwise, so this check is not sufficient, however, because other processes could conceivably create a new directory somewhere in the file system and allocate the inode that had previously been used for C. Process A is tricked into thinking that it accessed the correct inode. Nevertheless, the system maintains its integrity. The worst that it could happen that the wrong file is accessed. A possible security breach. but a race condition is rare in practice. A process can unlink a file while other process has the file open. And since the kernel unlocks the inode at the end of the open call, the unlock call is will succeed. The kernel will follow the unlink algorithm as if the file were not open. It will remove the directory entry for the file. No other process will be able to access the now unlinked file. However, the open system call had incremented the inode reference count. The kernel does not clear the file contents when executing the input algorithm and conclusion of the unlinked call. So opening process can do the normal file operations with its file descriptor, including reading and writing the file. But when it closes the file, the inode reference count drops to 0 in output. The kernel declares or kernel clears the contents of that file. In short, the processes that had opened the file proceeds as if the unlink did not occur, and the unlink happens as if the file were not open. Other system calls will continue to work for the opening process. So this is unlinking an open file algorithm or program for unlinking open file. See, in this program we have created a pointer array, character argument v, then integer file descriptor, character buffer array with size at 1024, then struct stat, that is variable stat buffer. If argument c is not equal to 2, then there is need parameter, that is if this condition becomes true then execute, otherwise fd is equal to open argument v, the file is argument v1, and open for read only. If file descriptor is equal to -1, then open fails and exit, otherwise unlink argument v1 is equal to -1, that is just file opened. If it is -1, then exit. Then if stat of argument v1 and stat buffer of this full statement is equal to -1, then stat the file name, that is a stat fails as it should be in argument 1, else the print stat is a succeed. Then fstat of file descriptor and stat buffer is equal to -1, then it print fstat fails, otherwise a fstat successful, while read fd buffer and size of buffer is greater than 1, then a read, that is open file, and print, that is the size of that buffer, and stop. This is the program for unlinking an opened file. So a process open file supplied as a parameter, then unlinks the file it just opened. The stat call fails because the original path name no longer refers to a file after unlink, but fstat call succeeds because it gets the inode via the file descriptor. The process loops reading the file 1024 bytes at a time. The printing file would be to the standard output. When the read encounters the end of the file, the process exits. After the close in exit, the file no longer exists. Processes commonly creates a temporary files and immediately unlink them. They can continue to read and write them, but the file name no longer appears in the directory hierarchy. If the process should fail for some reason, it leaves no trail of the temporary file behind it. Then file system abstractions. File system types allows the kernel to support multiple file systems simultaneously, such as network file systems or even file systems of other operating systems. Processes use usual unique system calls to access files, and the kernel maps the generic set of the file operations into the operations specific to each file system type. The inode is the interface between the abstract file and the specific file system. The generic inode, the generic in-core inode contains data that is independent of particular file systems and points to the file system specific inode that contains file system specific data. The file system specific inode contains information such as access permission, block layout, but generic inode contains the device number, inode number, file type, size, owner, and reference count. Other data that is a system specific includes the super block and directory structure. This is the figure inodes for the file system types. Suppose this is a system 5. There are the operations, system 5 operations: open, close, read, write. Similarly, the remote system has operation remote open, remote close, remote read, remote write, and so on. These are the generic inodes. So whenever any operation done by any inode from any system, it it shows there in their inode table. Suppose only open system call is done by inode from system 5. It gives the that inode number in system 5. Similarly, the generic inode has call the system call, suppose are open, and its number, reference number stored in remote inode, and so on. This is inodes for the system file system type. So this figure shows that generic in core inode table, there are two tables: file system specific inodes. This is file system specific inode. From suppose there are two file systems, that is system 5 file system and remote mode. So the latter inode is presumably contains enough information to identify the file to remote file system. A file system may not have inode link like structure, but file system is specific code manufacture an object that satisfies Unix file system semantics and allocates its inode when kernel allocates a generic inode. So each file system type has a structure that contains address of the functions that performs abstract operations. When the kernel wants to access a file, it makes an indirect function call based on the file system type and the operation. Some abstract operations are open a file, close it, read or write data, return an inode for file name component like name I or I get, release an inode, update an inode, check access permissions, set file attributes, mount and unmount file systems. So file system types allows to kernel support multiple file systems simultaneously, such as network file system or even file system of other operating system. Processes use usual Unix file system call to access files, and kernel maps a generic set of operations into the operations specific to each file system type. The inode is the interface between abstract file system and specific file system. A generic in-core inode contains data that is independent of particular file system but points to a file system specific inode that contains file system specific data. So file system specific inode contains information such as access permission, block layout, but the generic inode contains device number, inode number, file type, size, ownership, then reference count. Other data that file system specific include
Sir, present.
the super block and directory structures. Okay, this is completion of your fourth chapter. Now we have completed four chapters. In next lecture we are going to study a next chapter. Okay, we stop here. If you have any query, please ask. Otherwise, write your roll numbers and leave the session.